Hi, in this video we're going to fail to do something for once, but the reason why we're failing might also be interesting. So let's see, with that spoiler out of the way, what we can do. So we're trying to construct free things because we like free stuff, right? And we've seen that it makes sense to ask for free stuff whenever we have a forgetful functor from some structure to less structure. So this seems to be a promising situation like this, right? Where we have monads on some category C, and we know that we can forget about the monad structure and just get an ordinary endofunctor. So there certainly is a functor which goes this way, which just forgets about the return and the join, right? So we could certainly hope that there is a functor going this way, which is left adjoint to this. We've seen that this is how we get three things by having left adjoint to the forgetful functor. Right. So let's see if we can do this. So the idea would be that we want to add in a return because an arbitrary functor does not have a return, and we want to add in a join in some sense because an arbitrary functor does not have a join either. Right. So let's see. So here we have a functor f, and we want to add in the structures. I'm going to do this with the data type where I'm saying the free monad on f. Well, it should go from set to set, so I'm only restricting to set now for simplicity. So given a set x, I'm going to say what this is. So it's either going to be a return, which then has a value of x. So I'm going to add this in freely, or it has to be the original monad because I want it to extend the original one, right? So it's f of x to 3m of x. Okay, should have done this in the module. And should have said act, so not the actual objects. Okay, so that's the definition. And now I could hope that this is actually a functor at least before I even start to consider if it's a monad, right? So a free monad functor should be a functor from set to set. Let's see if we can prove this. So we need an action on objects. That's just going to be the thing we defined. Okay, and down here we need an f map. So we get given an f from A to B and something in free monad of f of A. And we can pattern match on that x and see that it's either a return or an f layer, right? So if it's a return, then we're in luck because we have an x in A and we have a way of turning A's into B's. So here we can just use return f of x, right? And if we have a layer, well, we know that we need this thing to preserve the identity, so we have to map this to a layer. Right. But here now, right, so here we have an f of A and we want an f of B, but we know that f is a monad as a functor. That's the whole point. It's not a monad. So we can use the f map of f to turn that x into an f of B, right? Okay, these are also possible to do. They're quite boring. Let's move on to the fun stuff. So we have a return by construction. So all we need for this to be a monad is a join, which before we even start thinking about naturality, etc., this need to have an operation of this type. Right? Where we're taking two layers of join and mapping it to one layer of the monad. Okay, so what is this? Well, we can pattern match on the x. If it's a return, then this x is now from the inner layer, so we can return it immediately. This is what we did before with join. And if it's a layer, then, well, we have that it is f of something. So we can't get rid of that f, right? But if we do another layer, then we get to produce an f. But in order to do that, we could try to f map using f, but then we need a way to escape from this monad, which doesn't seem possible, right? Because we don't have any, we only put things on, we never take things off. So we see that we made a mistake in this definition when in the layer we only allowed one application of f, right? So this is like when we did the category or the free monoid, if we'd only allowed one concatenation or one composition. So we have to allow arbitrarily many of these. So this is not possible. So it's stuck here. So let's try this again. But this time I'm going to say that rather than having an x directly here, because I can always get an x by doing return, like the unit, I'm going to have another layer of free monad inside this f. I get some errors. Let's first fix this up. Here the problem is that we now go from the free monad away, so this is another recursive call, and it's not clear to Agda that this is terminating, so let's lie. We say that it is. And this is not strictly positive, so let's tell Agda to shut up for now. Okay. And now let's see if we are stuck here. So here, now we can just do another recursive call. Right. Okay. And then again, we don't know that this is terminating, but it probably is. So that seems okay, except that we had to turn off certain things, right? So these termination checks and this positivity check. And actually, this is bad. It's not just Agda not being clever enough. So let me show you why. I do another definition of a bad data type. We have one constructor, and it says that if I have something from bad to false, then I get something in bad. And again, Agda complains in the same way, so let's make Agda shut up. Okay. So now let me show you what the problem with this is. And the problem is that if you assume this, then you can prove anything, which sounds great, but it's not so great if you actually want to trust your proof, right? So step one is to define an application for bad, which takes a bad and a bad, gives me back a bad. So what I'm doing secretly is I'm seeing this as a kind of untyped lambda calculus, and the fact that this type is isomorphic to this one, because that's always the case when you have a single constructor data type, right? That you're always isomorphic to its domain of the constructor. But okay, so here pattern match an X, and there's only one constructor, so it must be this one. Okay, but then I can just feed the argument to f in order to get a bottom out. That's the point. Okay, so that looks a bit strange, but maybe that's okay. Problem now is that I can actually define an element of bad. And how do I do it? Well, I use the only constructor I have. And I should say that this is supposed to be bad. Right. Okay, so here I get given a B. And how am I going to make a bottom? Well, I can just apply B to B. And now I'm really in trouble. Now I can define an element in the empty type by just applying omega to itself. And if I now try to run this program, then I'm going to be running it for a very long time. Maybe I dare to do it. Okay, so it's running, and if I try to do something else, you see that Agda is busy trying to run this infinite loop. So what happened? Well, I allowed this bad data type definition, which meant that I could sneak in non-terminating programs into my type theory, which meant that I could prove false, which means that all my other proofs would be useless, right? Because I never know if I now haven't just used this segfault to embot a limb to prove whatever I want. So we can't really afford to allow to turn these things off. Okay, now I turn Agda off. We can't afford to turn off the positivity checker, because if we do, so now it's okay, because now I get an error that this is not allowed, right? So Agda is not letting me do this. But in order to define the free monad in general, I need to turn off the positivity checker, because I don't know what this functor f is doing. F could really take this thing and put it to the left of an arrow, like we did here, right? At least to the left of multiple arrows, because it still has to be functorial, right? But so if we had free monad for every monad, then we would also have something like this bad data type. And if we did that, then we could prove false. So we can't do that, right? So free monads don't exist in general. That's the end of the free lunch. What we have to do instead is we have to restrict our attention to the functors where free monads do exist. So basically where this thing is disallowed, where we have recursive occurrences on the left of an arrow like this. So that's what the strictly positive is about. That have these so-called negative occurrences of the thing we're defining. So that's what we're going to do in the coming weeks, to look at classes of functors and data types where this does make sense.